Hello everybody, my name is Danielle Weigel, and today we are going to be working through Exam 2 for the class Transport 2. The situation we have today is that we are going to be working through some dimensional analysis to identify dimensionless groups needed for situations, and then we are also going to simulate an experiment in how to determine the relationship between those dimensionless groups. In this video, we are going to be focusing on the first part with the dimensional analysis. So the situation we have here is based off of the experiment conducted by Sherwood and Gilliland, as you can read on the screen, that established the correlation for evaporative mass transfer of a liquid flowing down the inner walls of a vertical cylindrical pipe. In this experiment conducted by Sherwood and Gilliland, they determined three dimensionless groups and their relationship that allowed them to and the relationship between them. So we are going to basically do the same thing and show that it can be done. So the first thing that we need to do in order to start our dimensional analysis is that we need to identify which factors could affect the situation we have at hand. So the first thing, switch markers. So the factors that will be affecting the system are the ones related to the physical tube, which is the diameter of the tube, represented by D. We will also have the parameters affecting the liquid flowing down the tube. So that can include the viscosity of the liquid, it can include the flow rate of the liquid, and it can also include the density of the liquid. And then aside from that, we have the parameters affecting like the interactions between the gas and the liquid. And that is the Maxwell-Stefan diffusion coefficient and the mass transfer coefficient. So now that we've identified these factors, we're going to need to build a dimensional matrix. And in order to do that, we first have to identify the base units that are used to describe each of these parameters or factors. So for the diameter of the tube, we can look at meters. We'll just use SI units. For viscosity, we have kilograms per meter second. For the velocity or the flow rate, we have meters per second. For the density, we have kilograms per meter cubed. For the Maxwell-Stefan diffusion coefficient, we have meters squared per second. And for our mass transfer coefficient, we have meters per second. Now that we've identified the base units, we can start building our dimensional matrix. So we will be looking at meters, kilograms, and seconds. Our distance, our mass, and our time. We'll just get rid of that. But so the way that we're going to create this dimensional matrix is to identify which exponent would apply to each of the units involved in these factors. So for our diameter, we have meters, just meters, so that's a 1. For viscosity, we have -1. For velocity, we have 1. For density, we have -3. For the diffusion coefficient, we have 2. And for the mass transfer coefficient, we have 1. Then for the mass, we have 0, since it's not involved in the diameter, a 1, 0, 1, 0, 0. And then for our time parameter, or the time unit, seconds, we have 0, -1, -1, 0, -1, and -1. So we need to determine the uniqueness of each of these columns, and which is the rank of the matrix, And we can do that in Python. So we will do that in a second. Alrighty guys, welcome over to Google Collaboratory, which we're using to run Python on. And we're going to determine the rank of our matrix. I've upgraded since my last video. We're going to add a little box down here with the references so that anybody watching can see pretty easily what is going on. The only thing that we're going to have to import tool-wise right now is NumPy to support our matrix and our rank function. So we will import NumPy as NP. And then, as you can see, the matrix rank function is right here below me. So we will write NP dot linear algebra and then matrix rank. And I just copied over our matrix into a notepad document, so I can just copy it in here really easily. Voila. So then we can shift enter and we see that the rank of the matrix is 3. So each of those rows are unique. So now that we've determined that the rank of the matrix is equal to 3, we can determine how many dimensionless groups we need. And that is calculated by I is equal to the number of total groups minus the rank. And since we have 6 groups here, that is our n. And that leaves us with 3 pi groups. 3 dimensionless groups that we need to identify. When picking our dimensionless groups, and identifying our dimensionless groups, the first thing that we need to pick is our standard groups, and we are going to look at the mass transfer coefficient, since that is usually determined experimentally, and since that has meters per second and velocity has meters per second, we are going to use that as our second one, just because it'll be more efficient for us. And then our third one, let's just go with viscosity. So those will be our 3 groups, or standard groups. And then we need to incorporate all the other parameters that could affect it. So we have Kc, which is our mass transfer coefficient, we have the diffusion coefficient, density, and the diameter. Woo. And we have those for each of those. And then in each of those equations, we will have to determine the relationship between each of these so that they actually cancel out to be dimensionless. So we will give these ABC. Since Kc and velocity have the same units, these will end up being the same, so I'm just going to leave the same variables. So we have ABC, and then for the third group, we have ABC, D, E, and F. So let's go ahead and determine what A, B, and C are. When we look at pi group 1, Kc has the units of meters per second. The diffusion coefficient has meters squared per second. Density is kilograms per meter cubed. And the diameter is meters. So when we look at the 3 different units that we have, meters, seconds, and kilograms, we first look at each of these terms. Kc will just be a number. Since we have meters here, it's 1. Since we have a 2 in the next group, it will be plus 2 A. And then we have a -3 here, so -3B. And since we have just the 1 here, plus C is equal to 0. For seconds, we do the same thing, a -1, -B, 0, and 0, since that's not involved there. And then kilograms, we have a 0, a 0, a 1B, and 0. So then we can use this to start determining our, this is C, my bad. No, this is B, this is A. Yeah. So then we can use that to start determining this. B is equal to 0. When we simplify that down, we get A is equal to -1. And then when we rewrite this equation, we get 1 plus -2 plus 0 is equal to -C. So that means that C is equal to 1. Now that we have each of those exponents identified, we can write out what our dimensionless groups will be. So for pi 1 and pi 2, we have, for pi 1, we have Kc, and then since the exponent for A is -1, our diffusion coefficient will go on the bottom. Since our B is 0, the density will just be equal to 1 and not involved in this unit group or dimensionless group. And then the diameter is to the exponent of 1, so that goes at the top. And then we follow the same trend for pi 2. So we will have the velocity, the diameter, over the diffusion coefficient. Next, we need to identify the third dimensionless group units and exponents. So if we look at those units, we have viscosity is equal to kilograms per meter second. And we have, just like before, the diffusion coefficient is meters squared per second. Density is kilograms per meter cubed. And diameter is meters. So we will have this again. And then these numbers are all going to transfer down. -A, -3B, and C. And 1B. The only thing that will change is the representation of these units. So we have 1 for kilograms, -1 for meters, and -1 for seconds. So then we can resolve these equations. We will get B is equal to -1. A is equal to -1. And then when we rewrite this equation up here, oops. We will get that. And that means that C is equal to 0. So then we can go ahead and write out our third dimensionless group. A is equal to -1. Oh, we'll include viscosity first. I guess these would have been D, E, and F. Alrighty. So we know that D is equal to -1. So once again, the diffusion coefficient will go here. And then E is the density, that is also on the bottom. And then since f is equal to 0, that one is not involved. So here are our 3 dimensionless groups that we calculated, and the 3 groups that were used and identified by Sherwood and Gilligand are the Sherwood number, which is equal to KCD over DAB, which is our first one. Our Schmidt number is equal to the viscosity over the diffusion coefficient times density, which is this number. And then our Reynolds number is actually equal to the velocity times the diameter times density over the viscosity. And so when you look at our 2 dimensionless groups that we have right here, you can see that all of those variables are included in here. And what you'll find is that if we divide the dimensionless group 2 by pi 3, we will get the Reynolds number. So that shows us our dimensional analysis and how we get our dimensionless groups. So in the next video, we will talk about how to determine the relationship between those 3 variables. See you in the next one.